next speaker, we have Bottini. It's going to be talking about topological order enriched by non-invertible symmetry via N-channel condensation.
Oh, this work.
Yes.
Okay. So thanks a lot for inviting me to speak, and thanks for coming in these extreme conditions. And yeah, today I'm gonna tell you about this work, which is based on. Based on. I have to point it where?
No, it was for it. What?
Oh,
Okay.
Right there. So based on this paper that came out recently and in collaboration with Clement Delcamp, which is at IHES and somewhere here in the audience, and Edwin Hen, Campbell McLaughlin, and Dominic Williamson, which are at the University of Sydney. And the setting, is topological order in 2+1 dimension. So a theory of topological line effects called anions. And it's well known that in the presence of a global symmetry given by a group G, which I will assume to be finite in this talk, then we can speak about symmetry enriched topological order. And for both of these two things, there is a well-known mathematical formulation. So topological order is captured by a unitary modular tensor category for P. And symmetry-enriched topological order is captured by this G cross-braided fusion category denoted in this way, which we also heard from in the first talk today. And the question I would like to address in this talk is how we generalize this when the enriching symmetry is not described by a group, but is in general a non-invertible symmetry. And okay, I want to stress that there is also this paper on a related topic that came out last year by Clement and other collaborators, and also two very related papers that came out roughly at the same time, one by Brandon one after. And just to say, this is a natural asking about symmetry enrichment by a non-invertible symmetry is a natural question, at least from a perspective. The first one is condensation defects. So typically, the symmetries G that can enrich your topological order have as underlying zero-form symmetry defect is condensation defects. But it often happens that these condensation defects actually have non-invertible fusion pools. So this leads to considering non-invertible symmetry enriched topological order. And the other perspective is anion condensation, and that's what I will discuss today. So this is the plan. I will just very briefly review group G symmetry enriched topological order and describe how we obtain G symmetry enrichment via anion condensation, and then move on to this non-invertible symmetry enriched topological order, which, as we will see, is actually described by an hypergroup. I will describe what it means to have an hypergroup grading and an hypergroup action, and then I will conclude. Okay, so what does it mean that a topological order is described by a unitary modular tensor category? Well, every object in the event C corresponds to some anion species, and this encodes two very important data, which are the fusion pools of the anions and their grading. And then, if you have a global symmetry G, this symmetry has to act in a way that is compatible with this fusion structure and with the grading structure. So these are known as these braided tensor autoequivalencies. And once you have a symmetry G, then in addition to the topological lines, the anions of the topological order, you can consider domain walls. It implements the zero-form symmetry G. So you have one domain wall for each group element. And a standard example is EM duality in the Tori code, which has these four types of anions, one EMF. And this EM duality is a zero symmetry that swaps ENF. So in this setting, apart from the anions of the underlying topological order, you can also talk about twisted sector lines. So these, for me, are topological lines that live at the end of one of these surfaces implementing the symmetry G. So I will call XG a line in the G twisted sector or a G effect line. And the mathematical structure capturing this thing is a G cross-graded fusion category. So this is something that in first instance is G graded. So you have one component G for every element in the group. And here V1 is just your underlying topological order, so the untwisted anions. While VG, with G different than the identity, precisely describes these G twisted sector lines that live at the end of a topological surface. And this G grading, this G grading has to be compatible with the tensor structure of the G cross-graded fusion categories, which means that if you take a defect line living in G1 and a line living in the G2 twisted sector, you multiply them, then you need to obtain a line that lives in the G1, G2 twisted sector. And then we have the group action that then is described via these maps from the group to these graded tensor of equivalencies. And another important property is that this symmetry action is again to be compatible with the grading. So if you act with the symmetry G on something living in grade X, then you need to land on something that lives in grade GX to the -1. And finally, in this case, also the grading is twisted by the G action. So the grading between two lines X and Y, if X lives in sector G, then acquires an action by the symmetry. And another thing you can do once you have like G cross-graded diffusion category is consider like its G equivalentization, which physically just amounts to gauging the zero-point symmetry in your theory. And I will denote the theory you obtain after gauging in this way. And its objects, I mean, the topological lines are just lines of the before gauging, equipped with a series of maps from TGX to X. And this physically captures the fact that you need to have gauging variant things surviving this gauging procedure and also as well symmetry. And two important things that arise in this G cross-graded extension on symmetry and topological order are symmetry fractionalization and discrete torsion. So symmetry fractionalization means that your symmetry G can actually act in a fractionalized way on anions. That, for example, G acting on a composition of G acting on an anion A can acquire these projective phases. And this is classified by this homology class, where A is the group of abelian anions. And physically, the interpretation is that you're decorating the junctions of zero-point symmetry defect by an abelian anion specified by this homology class. And then you can see this fractionalized charge as due to the braiding between your anion A and this anion you're decorating the junction with. And then we have discrete torsions. So this just physically stacking your topological order with an SPT for your global symmetry G. So this is captured by this homology in H3G1. And this is encoded in the associativity of the G twisted sectors.
Yes. Sorry, so think of this as the capture, the symmetry of a three-dimensional theory.
Yeah, we are in the plus 1D.
Where
we have
the theory for symmetry is discrete finite G.
Yeah.
And then the lines can be any structure.
Yes. But in particular, A.
So they have an action of G.
Yeah.
So that one I can think of. I start my theory for symmetry with the coordination one. I started, but I crossed the line. Then I get this projective phase.
Yeah, you're decorating the junction of with us, yes. But it's importantly,
and then the braiding, we think of it as I braid them, but when I braid them, one of the lines crosses the G. The braiding style.
Yeah, Yeah, it's exactly that. Like you have to imagine that when like y passes past surface, it becomes yeah.
Okay.
So here compared to the normal gradient, when you're swapping x and y, x is
Okay. Thanks.
But here, importantly, like A is abelian anion, so it's like a proper group conform symmetry. So if you decorate the charge by abelian anion,
Okay.
not the full set of anions.
Thank
Okay. So one way to obtain this,
Sorry,
yeah,
is just a restriction or a yeah. Or generating.
I think it's it has to be an abelian anion because you want, so these projective phases are in one, and it's a property in an MPC that whenever you have phases that satisfy the group diffusion, so you have to think eta A, eta B is eta C if A and B choose into C, then this one phase can be expressed as the gradient with an abelian anion, but the fact that it always gives you one phase restricts the anion to be a P. So yeah. Okay, one way to obtain these G cross-graded diffusion categories is via anion condensation, which is something that is classified. So patterns of anion condensation are classified by a condensable algebra. And roughly this means a set of anions that are bosonic and you identify with the identity. And once you do this procedure of anion condensation, you have access to a new topological order, which I call BA, where now the excitation are the modules of this condensable algebra A. So these are pairs M rho, with M is an object in the original topological order B, and you have maps from M to A into M. And you can have two types of excitations in this B of A, what are called deconfined excitations, which are the local modules of A. This means only anions that grade trivially with the anions you're condensing. And so these are genuine lines in the resulting theory. While the rest of the excitations are confined because they come from anions that grade non-trivially with the algebra you're condensing. So these are the non-local modules of A. And if this algebra A you're condensing forms rep G, the sense that it decomposes in this way as objects, so like that's the regular representation, then in general, this BA you obtain after condensation is G cross-graded. And moreover, you can show that once you do G equivalentization in this theory after condensation, you go back to the original topological order you started with. So let's do an example, which I will follow from the top. This is the S3 quantum double model. I denote S3 in this way, where R, the generators are R and S, S is a transposition, R is a cyclic permutation. And the topological order corresponding to this S3 quantum double model is the Drinker center of SC. So this captures the charges and fluxes of this S3 gauge theory. And importantly, this contains rep S3 as a subcategory. This describes the pure charges in your S3 quantum double. So let me denote rep S3 inside here as 1 E pi, where E is the sign in rep and pi is the two-dimensional rep of S3. And then let's consider condensing this algebra, which I denote ACP, which is given just by 1 plus E. And notice that this is associated to rep C2 in your topological order. So if you condense this AZ3, then the local modules, the deconfined excitations, are given by the Z3 toric code, where the excitations are described by the Drinker center of Z3, while the local and non-local modules, so the general A modules, are described by this relative center of Z3 in S3. And notice that here, when one can show that this actually has a Z2 symmetry, in this case, it's just given by S3 mod Z3, which is nothing but charge conjugation. So in this Z3 topological order, you swap E bar with M and M bar. And then if you do equivalentization with respect to the Z2 charge conjugation symmetry, then you go back to the center of S3 we started with. So this is this general thing I was showing here in the example. If you start from the center of S3, you condense this algebra which is associated to MC2, then you obtain a theory that has a Z2 symmetry that you can take to go back to the original. Is it possible to move? I'm scared it will just quit the presentation, but oh. Okay. Nice. Okay. But in general, you can condense more general algebras than these ones of type RepG. And remaining in this example, let's consider condensing this algebra, which I call AC2, which is divided by 1 plus pi, where pi now is taken to be irrational. And in this case, the local modules are described by the toric code. So again, I use 1E mx for the excitations. And the A modules confined and deconfined are described by the relative center now of 2 in S3. In particular, we have two confined excitations that I call C1 and C2. And the question is, what is now the symmetry in reaching this topological order we obtain after condensation? In the same way, before we had this C2 charge conjugation symmetry coming from S3. What we propose is that this is an hypergroup symmetry, which is associated to taking out the double coset of S3 by Z2, which is a non-normal subgroup. And the first thing to notice is that this topological order we obtain after condensation naturally decomposes over these double cosets. So in this case, this has only two components, the identity, which is just Z2 itself, and then one non-trivial component, which is the rest of the elements in S3. Then we can say that the toric code anions, the confined excitations, belong to grade 1, while C1 and C2 belong to the only non-trivial grade specified by the non-trivial double coset element R. So what is this hypergroup thing I'm talking about? So this is built from a set Ki, where you have a fusion structure of this type, K1 and K2 is somewhere subconstants K3, where these are real numbers that have to be greater or equal than 0 and which sum to the identity. So it's some sort of probabilistic version of a fusion ring. And importantly, to a double coset, like the one we are considering, in our example, you can always give the structure of an hypergroup with this particular multiplication. And notice that if you pick n to be normal, like in the case of the charge conjugation example in S3, then this hypergroup just reduces to G mod n as we compare the previous statements. So in our example, we have only one. We have only one non-trivial hypergroup element, which is this R here. And if we take the, in this case, the only. In this case, the only non-trivial product is this one. I don't know, it's something like that. Yeah.
No, I just started.
It's not that what you right now. I think if we just stop this. No. No.
I think you just made it.
I made it go on again.
Yeah.
All right. Now it's stop, and I go like this, and it should be fine.
Yes. So the only non-trivial fusion rule is of this type. So R with R turns out to be 1/2 of the identity plus 1/2 R. So in this case, the non-trivial constants, which are called the structural constants of the hypergroup, are both given by 1/2. And then, okay, we can make a bit more specific what it means that the topological order that we obtain after condensation is created by this hypergroup. And the compatibility condition is as follows. So if you take an element which is in grade K1, and an element that lives in grade K2. These have to be simple objects. And then you take their tensor product and you project on the outcome labeled by the component K3. And you take the ratio of the quantum dimension between this projection and the total quantum dimension of the tensor product. Then this has to give you the structural constants of the hypergroup. This has also appeared in the maths literature before. And we can check this is indeed the case in our example. To see this, you need to know the fusion rules in the field of the condensation. And you can verify indeed you obtain 1/2 given these fusion rules for the lines C1 and C2 that live in the grade R.
You speak louder.
Is the product social?
Yes, I think so, yeah.
That's what I'm gonna see.
Yeah,
Also have first.
yeah. Well, if there's, yeah, any containing the element. Huh? Yeah. I mean, it has objects that fusing with them as an outcome, at least the identity, plus possibly other elements. Okay, so the first thing I mentioned is the fact that we have this gradient by the hypergroup. And now what we want to find is also a symmetry action. And the way we define this hypergroup symmetry action is by a composition of factors. So T is the hypergroup symmetry, and we start with the topological order after condensation. And this is basically obtained by composing the forgetful factor, which maps us back to the theory pre-condensation, with the induction factor that maps you to the theory after condensation. And one can check that T, defined in this way as the composition of these two maps, actually decomposes over the hypergroup. So in this case, we have T1, which basically acts as the identity, and then one non-trivial action TR. And it turns out that in this case, the non-trivial hypergroup action on the anions here is given as follows. So it's clearly a non-invertible action. For example, the identity is 10 to 1 plus E. C1 is 10 to M plus S plus C1. So like in general, one anion can be sent into the sum of multiple others. And similarly to the compatibility condition between the tensor product and the hypergroup grading, there is also a compatibility condition between this hypergroup symmetry and the grading, which is defined here. So for it, we need to define an adjoint action where we just use the product of the hypergroup and by conjugation. And then this defines a new set of structural constants, which I call A for this adjoint action. And then in this case, the compatibility condition is that if you act with what is called the regular object in sector K2 with the symmetry K1 and you project on K3, the quantum dimension of this versus the total quantum dimension of the action gives you these adjoint structural constants. Yeah.
Are you associated topological line operators with elements of
It's more surface effects. Well, yeah, but then yeah.
But I have some say for this about the check the coefficients are integers of topological operators because I thought it was important that we can only multiply by integers the symmetry operators so that we can find a twisted over space that get functions.
Yeah, so there is a point, I mean, in some sense, this hypergroup symmetry as underlying surfaces, also condensation surface types. So in this case, in this example, when you act on the identity, you get 1 plus E. This is exactly the action that you would obtain if you consider the condensation surface where you condense the boson E. So we believe this hypergroup action is exactly the action of this underlying topological order. And you can also show that gauging actually the identity surface plus this S surface brings you back to the center of S3. But this product of the hypergroup is not exactly on the nose the product of the condensation surfaces, even though it's compatible. And so I am not completely sure if you can always rescale this product of the hypergroup to an integer constants. I don't think so. But for this compatibility condition, it's really important that you have these non-integer constants showing up from the hypergroup. I think somehow it's the difference between taking the parallel diffusion of effects and looking at also junction of effects, where this hypergroup structure arises, because basically it's what we are getting the fixed sector lines of the condensation surfaces by. Okay, how much time?
About 12 more minutes.
So actually this symmetry action that we define in this way can be given mathematically the structure of a monad. And for me, I'm not a mathematician, it just means functors from C to C that in particular have a multiplication rule, so this composition. And we believe that somehow this multiplication rule of the monad T is what encodes a generalized symmetry fractionalization. So notice that, for example, if for in the normal case, this just reduces to isomorphism between K1, K2, K1, K2, which is where the symmetry fractionalization shows up in the group case. And once you have this gadget, you can also gauge the non-invertible symmetry, similarly to when we do G equivalentizations, which actually requires promoting T to a off monad, so putting additional structures. And then the theory you obtain after gauging is obtained by looking at T modules. So you looked at the topological order after condensation, you take T modules and you go back to the original topological order. And there is also a generalization of what is known as the fixed point theorem. So in the group case, this tells you that the rank of Vg, so the number of simple lines that you have in each G-twisted sector, is given by the number of anyons in the underlying topological order, which are fixed by reflection. So the generalization in the hypergroup case is that, again, in like the number of simple objects that live in grade K are just given by the objects S in the underlying topological order, for which there is a map between the action of TK on X with S. Then you compute these on spaces, and the dimension is the rank of the K twisted sector.
Yeah. So for this case, can you get like a non-abelian anion appearing in the symmetry fractionalization? Because,
yeah, it's a good question, and at the moment we don't know. It didn't arise in the examples we looked at, but I don't want to make general statements.
I think one collaborators actually studied that example where you get non-abelian anions.
Yeah, I imagine now it's possible. But...
You know what the example is? Like which?
It's basically related to this condensation from S2 to level 10 to spin by level 1. If you try and do that, then
okay.
So the surfaces in that area are really trivial on all the juices in the oceans between the trivial surfaces.
Okay, and let me just flash very briefly that we can also compute this action with a cube algebra approach. So again, we consider the quantum double model for S3, and in this case, local excitations in the original topological order are described by modules over the cube algebra, this cube algebra, which is generated by these elements. Everything lives in S3. And this, of course, recovers the simple objects of your simple modules are just the objects in your 3-5 center. And once we conduct our algebra AC2, the local excitations are given by modules over this restricted cube algebra, where now the elements here are restricted to live in C2. And again, if you just take also X living in C2, this captures the deconfined excitation, so modules over 2 C2, which is just the toric code, while the rest of the sectors organize into the double poset. And here simple objects are labeled by an H orbit and an irreducible representation of the stabilizer. And in this case, the non-invertible symmetry action can be equivalently computed by looking at these particular cubes, where now X lives in S3 and G in the hypergroup element K. And basically, we compute the symmetry action by multiplication by these particular cubes by embedding everything in the original cube algebra. So the idea is that the action of some anion here in the resulting topological order after condensation can be computed by using multiplication by this cube on the corresponding minimal central idempotent in the reduced cube algebra. Okay, and just let me mention that here I discuss only this group example where we condense from the center of S3 to the toric code. And for this construction, it was crucial that H is a subgroup of G. And indeed, the hypergroup enrichment that we get in the topological order after condensation is given by this double poset of G by H. So we expect that this construction can actually be generalized to more general patterns of anion condensations. So where you start with the center of C, and you condense to something that has deconfined excitations described by the center of D, where D is a fusion subcategory of C. And then again, the topological, like confined and deconfined excitations will be captured by this relative center of D in C. And to these fusion rings, we can associate an hypergroup, and then we can take the quotient, and this will be an hypergroup that enriches this relative center. So again, the symmetry action, if you have a condensable algebra such that the A modules that give this relative center and the local modules give the center of D, then would come similarly from this kind of composition. Okay, so just to summarize, I try to put here the sort of G cross-braided usual story that we expect all the properties. And what we propose is the equivalent in this hypergroup enrichment. So the compatibility between grading and fusion, the compatibility between grading and action, the fact that you can take equivalentization, and then symmetry fractionalization, discrete torsion, and this fixed point theorem. And so just to conclude, let me say that in this case, we use this anion condensation to naturally land on this topological order enriched by non-invertible symmetry that we formalize as this hypergroup equivalent hypergroup graded fusion category that generalizes many of the features you have in the G cross-braided story. Now, I would like to stress that even though with this construction, somehow we start backwards, because we start already with the theory you obtain after where you would obtain after equivalentization, and you go anion condensation. So you don't start directly, you start somehow from the final answer. And we believe all these features here will arise in a more intrinsic way if you just start with some topological order and you ask what are all the possible hypergroup enrichment that you can have. And then presumably there will be at some point a classification of such gadgets in the same way we have a classification of the possible cross-graded extensions that you are starting from some topological level. Yes, that's how it is.
Would it be correct to say that the symmetry is really some fusion 2 category, but the hypergroup is some convenient packaging of that and the symmetry action?
Yeah. Yeah, I think so. So in a sense, I mean, you can have a full fusion 2 category story, which is what is described by, like in this previous paper by Clement that I cited at the beginning, where in that sense, they think of, I studied some topological order. I do one condensation, which is the gauging of some one for symmetry. And then the dual gauging to go back would be the gauging of some surfaces. So this would be described by an algebra in the 2 category that you obtain after condensation. And somehow, like this is, I don't know, it's the same of G cross graded, like you're really looking at the twisted sector, at enriching your underlying topological order with the twisted sector lines that live at the end of these surfaces that ultimately are what implement the gauging in the 2 category picture.
I just wanted to understand the last, the slide I did for this.
Yeah.
So the formula is like this, say, the formula on the lower right is like, yeah, or is it this?
In the lower right is random. We have a proof for this. We have it in the, no, we have it in the specific case, it's the specific pattern of condensation where we go from the center of G to the center of H. And for this hyperproof given by the double quotient. In generality, this is conjecture to expect that in the cases where you go from center of C to center of our category, something analogous to work. At the moment, no.
Well, that corresponds to the A3 obstruction for the generalized interval.
Yeah, good question. And we don't know at the moment. Because again, from this thing, I stressed that like we are not starting from a topological order and asking what are all the possible hypergroup enrichments that I can put on that. And then this would presumably have a series of obstructions and solutions to this obstruction, similar to the G-prosperity case. We already start from the final answer. So going back, we know for sure that there is the hypergroup enrichment, and therefore there is no obstruction that shows up in what are the enrichments. And we have some conjectures, so maybe we can calculate it.
I actually had a question.
Yeah.
Was you know, in the invertible case, there's a story about just a Hilbert space realization. Symmetries just intensify Hilbert space acting on site. Obviously, that would have. So have you thought about like just lattice for space generalizations and what how these symmetries generalize to that? Obviously, not many unitary.
Yeah, I haven't thought particularly about that. We have some like this construction, but I mean just writing parties with like the quantum double G realized condensation, but apart from that, I don't really thought.
Okay. Okay, one more question and then we'll go to
And you have an enrichment which copy this normally, then you want the light to go. And you can see what.
Like you mean starting from a case where I can do ion condensation and then I cannot go back?
So you always start from some association and extension.
Yeah.
Data extension.
Yeah.
But if I want to work, we have a virtual set with some grading. I think about the equivalent card because there is some.
I think this would be analogous to this question, like what would be the like the analogous of the H4 obstruction that you have in the G-prosperity case. But somehow we have already, I mean, this doesn't really show up in our case because the extension is guaranteed to exist. So we don't have at the moment that the theory of obstructions to the extent of this thing. Yes.
Let us thank the speaker again. Oh, yeah. I mean,
Stop here and you start there.
yeah.
Walking. No worries. And this is go full scale. Let me try to do this here. Yeah. Okay. I think we're good. I think we're good.
Now we have no way. Great. Okay, so our next speaker is Brandon Rayhaun talking about hypergroup symmetry and relative QFTs and chiral algebras.
Great. Thanks for the invitation to be here. Thank you for putting your bodies on the line to hear about hypergroups. Actually, maybe I can first start by answering my understanding of John's question. So indeed, the hypergroup corresponds to surfaces, but the hypergroup product is not going to just be parallel fusion of surfaces, because as you say, that leads to integer fusion coefficients. And then what you should imagine is that you have sort of, S3, S1, S2, and some trivalent junction that kind of links the surfaces, and you collapse this this bubble down to a point, and you'll get some number out here. Call it Pij or P123, and this does not need to be an integer because points are not beholden to the same integrality properties of extended operators. And this is the structure constant of this hypergroup. It's more like this bubble product rather than parallel fusion. Actually, that's kind of on my first slide. Anyways, so good. So this talk is going to be based on joint work with Terry Gannon. And I'm very grateful to both Clay and Leah for giving beautiful and pedagogical talks, which will prepare you very well for everything I have to say. And let me mention that these two papers appeared on the archive a few days before ours did. And as you'll see, they contained a lot of overlapping ideas. So our motivations evolved over the course of this project, but sort of one of the primordial motivations was, there's sort of two mathematically rigorous approaches to 3D CFT. One is the theory of vertex operator algebras. Oh, I can't wait. Works, yeah, okay. Okay. Yeah, so yes, one is the approach by conformal nets, and one is the approach by vertex operator algebras. And mathematicians have slowly been sort of exploring actions of hypergroups on these gadgets. And one of my goals, at least, was to try to understand, give a stronger physical basis for these hypergroup actions, and in particular, try and interpret them the same way we've come to interpret symmetries in terms of topological effects. Of course, 2D. That one more focus. So I'll just press it. As we know, 2D CFT is very closely related to 3D CFT. So in the process of answering the first question, we'll actually also be led to some small steps towards understanding what a theory of non-invertible symmetry enrichment for 3D TQFTs should look like as well. So before I get there, let me establish some shared terminology. So By a chiral algebra, I'll mean sort of the mathematical structure formed by the space of holomorphic local operators in a 2D CFT. Everyone's favorite chiral algebra is just the Virasoro algebra, which is for a generic 2D CFT, all that there is in the way of holomorphic operators. But for most purposes, it's not going to be good enough for what I want to do. So we want to consider particularly nice chiral algebras, one is rational. And these are chiral algebras which have a very nice representation theory. They have finitely many irreducible representations, and every representation decomposes into a finite direct sum of these. And the prototypical example of this is just the chiral algebra of the WZW model at a non-negative integer level. And also, we'll say that a QFT is relative if it lives at the boundary of non-trivial bulk TQFT in one higher dimension. Otherwise, we'll say it's absolute. And as I'll now explain, rational chiral algebras are going to be sort of my working example of a relative QFT, although much of what I say will generalize beyond just chiral algebras. So let me try to give you my perspective on, well, it's really the synthesis of many other people's perspectives on rational chiral algebras. So the nice property of these gadgets is that it turns out that you can sort of completely reconstruct features of the bulk just from boundary data. And so I'll just kind of colloquially refer to this as the bulk boundary correspondence. And this bulk boundary correspondence is a very mathematically sharp avatar that goes through tensor categories. So specifically, what you can do is you can, starting from the bulk, you can extract a modular tensor category, as Leah explained, which simply encodes the sort of algebraic properties of the anyons, the 3D TQFT. Let's call that category B. On the other hand, starting just from one of its chiral boundary conditions, you can also extract an a priori different, very nice category, namely the category of representations. And it turns out that this also forms a modular tensor category. And the sort of content of the bulk boundary correspondence is that these two modular tensor categories, one extracted from the bulk, one extracted from the boundary, are actually equivalent. And actually, not only are they equivalent, you can actually see the explicit equivalence between them. So specifically, suppose you take an anion in the bulk, and you want to ask how to associate a representation of the chiral algebra to it. Well, the thing that you associate to it is simply the Hilbert space of local operators, which live on the boundary on which this anion can end. And so that defines a kind of ribbon equivalence between the bulk and the boundary. And an example is, again, take B to be the chiral algebra of the WZW model, in which case the bulk is just Chern-Simons theory. Yeah.
This is survive from the state of any representations, rationalists.
You still have a notion of a representation category. Well, actually, at the very end, I'll give an example of the Yuan-Katz-Moody algebra, which is irrational, where I claim that almost all the words go through, except you just have to allow for infinitely many simples. So maybe ask me again then. Yeah.
In principle, there can be different rational chiral algebras that have the same bulk.
Absolutely. And
Right.
in fact, it's an infinitely many to one map.
Good. And so one of the interesting things that I'm claim is that the representation category of chiral algebra is
Yeah, exactly. That's right. I mean, the representation category is a very coarse shadow of the full chiral algebra. So you lose a lot of information, but the information you keep is precisely the data of the bulk. Good. So there's a kind of generalization of this picture, which occurs when you sort of equip your boundary with a choice of a group G that acts by its symmetries. And so kind of very non-trivial claim is that once you specify a G symmetry of the boundary, you actually for free get a G enrichment of the bulk as well. I shouldn't say for free, you have to work very hard to extract this. But let me just sketch for you the sort of first layer of data that you'll get. So my claim is that the way that an automorphism of V is implemented at the level of these pictures is it's implemented by a topological surface in the bulk that is anchored on some line junction L. You might ask, why do you need this surface here? Like, we're used to implementing symmetries by lines in 2D CFTs. And the intuition basically is that, well, in a very general setting, like for general algebra, if you choose an automorphism of the algebra, the automorphism in general commutes around the representations of that algebra. And the same is true for VOAs. So any symmetry of a VOA is going to commute around its representations. And in fact, more strongly, it's going to induce a Riemann autoequivalence of the representation category. And since we're sort of identifying the representation category of V with the category of anyons in the bulk, and because, as Leia explained, a Riemann autoequivalence is the same thing as topological surface, we can sort of extract from any automorphism of a bulk topological surface, and the role of that surface is precisely to commute around the representations, as you can see here. So if you take in an operator O in some representation VA, then the role of the surface is, when you act with the G symmetry, to sort of produce for you an operator in a different representation, G of A. Yes.
So if you just brought a line operator from the bulk to the boundary, what would that do on the V?
We'll get there. Yeah. Excellent. Okay, so there's much more data that you need to specify G enrichment, but it turns out that the rest of the data is also completely fixed by the boundary. And so we have a kind of analogous diagram here where you again have a kind of symmetry enriched bulk boundary correspondence, which again has a mathematically sharp avatar that goes through G cross braided tensor categories. And the statement is that starting from the bulk, you can extract this category of twisted anyons, that is anyons that live on the boundary of this bulk topological surface, or these bulk topological surfaces. And you can reconstruct that same category purely from the boundary by considering twisted representations. And I won't define for you what a twisted representation is abstractly, but again, you can sort of see roughly, intuitively what it's going to be. So the way that you associate a representation to a twisted anion A is you consider the Hilbert space of local operators that now lives at this junction. And what the word twisted here is sort of telling you is that if you take an ordinary local operator and you kind of take it around O, then you're going to pick up a monodromy due to the fact that it has to go through this line LG. Okay, and so the motivation is to sort of understand what replaces these concepts when you have a non-invertible symmetry, and the answer, as already anticipated, is you should replace groups with hypergroups. So to see why you're inevitably going to be led to hypergroups, if you think about this question, let me start a little bit more conservatively. In absolute 2D QFTs, we have this nice statement that symmetries are implemented by topological line operators, which in turn are described by fusion categories. So why not just start by considering topological line operators which live on the boundary? How do we get these? I claim in some sense that every fusion category of boundary topological line operators corresponds to a conformal subalgebra. And why is that? Well, basically it's the sim TFT. So if you have a conformal subalgebra, you can use it as the physical boundary condition of a kind of sim TFT construction. So that conformal subalgebra W is itself a chiral algebra, and therefore itself lives on the boundary of some TQFT. And the non-trivial claim is that by virtue of W sitting inside of V, that implies that there's this topological interface between the TQFT of W and the TQFT of V. And you can sort of extract a fusion category from this by studying the topological line operators that live on the world volume this topological interface. And sort of when you fuse this interface onto W, you'll recover V, and all the lines on this interface will become genuine boundary line operators on V. Yeah.
Can this happen in non-trivial way? The vertex algebra is just Virasoro.
No, so Virasoro, Virasoro is irrational in general, but you can ask about the minimal models. And the statement is that the only sort of lines that you get on, like, let's say C equals 1/2 Virasoro algebra are just the lines you get from pushing anyons in the bulk onto the boundary. So the boundary lines are just going to be exactly this icing category, this somewhere right on the boundary C2.
Did that Is the conformal subalgebra W just all of V in there?
Yeah, exactly. So yeah, so if you take W to be V, then this construction just produces the bulk lines for you. That's right. No, there's usually infinitely many W's. That's the sad thing. I mean, yeah, so this problem of studying conformal embeddings is a very like old and storied problem in 2D CFT. Like the easy examples are embeddings of current algebras, like WZW models, essentially. There's this whole zoo, which using this SimTFT picture can be, that entire zoo can be reinterpreted as a statement about fusion category symmetries. I don't know how interesting it would be to do that, but so that's, yeah, so, but there's no like general procedure to produce it like all the W's or something.
This TQFTW, is it usually larger than
Yes.
TQFT? Or
Yeah, it's larger.
it goes like the opposite way.
Yeah, yeah. You make the GUI bigger, its
Right.
representations get smaller.
I can see how I can go from suburbs first to lines, but I don't see the other as well.
Yeah, so you hand me some fusion category lines. The way I produce a subalgebra for you is I consider all the subspace of operators that are invariant under those lines. And then if you feed that into this, that'll like recover that category for you. There really aren't one-to-one correspondence. Okay, just to ground this in a concrete example. So as I said, the easy examples are these embeddings of current algebras. For example, the simplest example of a conformal embedding is SU2 level 4 into SU3 level 1. And in this situation, you can calculate that you actually get a Tombari-Yamagami Z3 category. And just to give you a flavor of how often people can sort of cheat and cook up these answers, a very useful tool is to sort of push lines from the bulk on either side onto this wall. So for example, the duality line of this Tombari-Yamagami Z3, sorry, can be obtained by starting with the fundamental Wilson line of SU2 level 4 and pushing it onto this interface. On the other hand, the three Z3 lines are obtained by starting with the Wilson lines of SU3 level 1 on the other side and pushing them onto the interface. And it turns out in this way, you can always get all the lines by pushing. You might have to disentangle a little bit, but you always get all the lines by pushing. Good. How much time do I have? Actually, do my phone so I can. Thank you so much. Okay. Good. So okay, so let's revisit how these fusion categories of boundary lines act on the genuine local operators of a chiral algebra. I'm going to use a sort of funny normalization where instead of considering the usual encircling action of a topological line, I want to consider that times 1 over the quantum dimension for reasons that'll hopefully become clear soon. And one interesting feature that arises in the relative setting that does not arise in the absolute setting is that this encircling action has a kernel. So specifically, if you are considering these lines that can be dragged into the bulk, well, when you drag them into the bulk, you can shrink them to a point, and then you get a factor of the quantum dimension, which cancels this one. And they just act as identity on all local operators. That answers your question about how the bulk lines act.
Yes.
I think it was your question.
Yes, I guess. Okay, it does, but I mean, in some sense, this is like the more basic case, right? The way the surface is.
Oh, we'll get to the surfaces. Yeah. Good. So, in a sense, the algebraic structure which is acting faithfully is not the fusion ring of C, but rather a sort of quotient of the fusion ring of C by the subring of anyons which can be pulled into the bulk.
Okay, wait a minute. So here, the hypergroup is appearing from the line operator and not the surface operator.
I'll relate it to surfaces in a moment. Yeah. I'm trying to show that you will be forced to consider the surfaces, basically, in some convoluted way of thinking. Right. So if you take a quotient of fusion rings, there's no way in general to make it a fusion ring again, but you can make it a hypergroup. And I think Leah did a pretty good job of defining what a hypergroup is, so I'll just speed through this. But basically, you should think that a hypergroup is a kind of generalization of a fusion ring where the structure constants are allowed to be non-integer in some sense. So more precisely, there's some distinguished basis, some multiplication rule where the structure constants have this stochastic normalization, and there's a unit and there's a notion of themes. And they really are a generalization of fusion rings because every fusion ring gives rise to an associated hypergroup by just sort of formally considering the elements of the fusion ring divided by their Frobenius kernel dimension. And then they'll automatically have this stochastic normalization. Pseudo-unitary, yeah, sorry. I'm assuming pseudo-unitary throughout. Good, and so Leah did this special case of a double coset of groups, but actually there's a general construction whereby you can take the double cosets of any hypergroup by one of its sub-hypergroups. And so the actual definition is not going to be used anywhere, so maybe let me just flash it and just say that this construction that Leah mentioned is a special case of this. But this is the construction I'm using on this previous slide when I say that the thing that acts faithfully is this quotient. It's the sort of double cosets of B inside of C. Okay. So as was pointed out, I should see surfaces at some point in this discussion. So to see how surfaces show up, let's imagine trying to pull a boundary line into the bulk. So sometimes you can do this, but the claim is that in general, if you try to do this, you cannot genuinely pull it into the bulk, but you can if you're okay with the line being trailed by a topological surface. And how do you characterize what surface is going to come out? So this is a little bit abstract, but the idea is that so the bulk lines act on the boundary lines by a parallel fusion. And mathematically, this means that the boundary lines form a B module category. And in fact, you can decompose the boundary lines into irreducible B module categories. And one sort of non-trivial claim is that when you do this decomposition, the sort of simple summands are actually labeled by precisely this hypergroup. So good sign that we're on the right track. And so the claim is, well, B module categories are in one-to-one correspondence with topological surfaces in the bulk. So in a sense, each of these graded components defines for you abstractly a topological surface of the bulk. And the claim is that if your boundary line belongs to a particular graded component, BRI, then the surface that you get when you try and drag it into the bulk is precisely this abstractly defined surface that corresponds to BRI, thought of as a module category. So that's very abstract, but there's a down-to-earth example which will illustrate it nicely.
Well, okay, how much okay, like you're choosing like a gapless boundary essentially.
Yes.
How much of that is essential for what you just said here? Like, so
it shouldn't be that essential, but in the way that I've just said it, it is kind of important because these gapless boundaries have this particular class of gapless boundaries I'm considering has this nice property that the bulk lines embed fully faithfully into the boundary.
okay.
That's not true of gapped boundaries like ever.
Right.
And I use that at various points.
But this general kind of the picture, so to speak, is
these should be the right pictures in general, but you have to say the right words. Yeah. No, it's just a module decomposition. And I only need to consider B embeds centrally inside of C. Yeah, absolutely. And that's precisely because it's a bulk to boundary functor. That's a general property of these bulk to boundary functors that they define these central embeddings. Yeah. So good. So let's go back to this SU2 level 4 example. So SU3 level 1 Chern-Simons theory has two topological surfaces. It has the trivial surface, which corresponds to the regular module category. And it has a Z2 charge conjugation surface, which corresponds to a non-trivial module category with one object inside of it. And so the statement is that in order to figure out how the lines of this Tombari Yamanagami category, what becomes of them when they're pulled into the bulk. You just have to understand how they transform under the Z3 part. So for example, the Z3 lines themselves transform in a triplet under Z3. And that means that when you pull them into the bulk, as you should expect, you get no surface dragging them. However, this duality line is a singlet under the Z3. When you fuse any of these eta lines onto this duality line, it absorbs them, and therefore it transforms in this non-trivial rank 1 module category. And that means that when you drag it into the bulk, it's trailed by the charge conjugation surface that we tried to illustrate. Good. So with this manipulation of trying to drag lines into the bulk, we can now reinterpret this encircling action. So take any line X, and just you start off with just X as a circle in the boundary, and then you apply this manipulation where you drag it into the bulk. It's trailed by a surface now. And next, let me just imagine pinching this circle X down to a point. Then I'll get a topological point operator on this surface SRI. But since it's a simple surface, it's only topological point operator is the identity. So you'll get some number times the identity. And let me call that gamma of X. So now we see these like dome-like pictures. It naively seems like they depend on X. But in fact, what you can show is that this combination, gamma X over dimension of X, turns out not to actually depend on X. It only depends on this surface which trails it. And in fact, it's equal to 1 over the dimension of the surface defined to be the number you get when you collapse a dome of the surface down to a point. Yes?
Good questions just about these pictures. That X with the bar under it, that's one of these cosines.
No, it's just my notation. I could have just written X.
It's just a notation for the bulk.
It's just a notation for the line on the boundary that corresponds to the line X is. Yeah.
Okay. And there was an earlier expression that these R's could be summed over, but is that not the case? There's a specific Ri for each X.
Yeah, that's right. So X belongs to some, we had this decomposition of the boundary lines into different pieces, and X will belong to one of those pieces, which is labeled by a single Ri. And that piece that it belongs to determines which surface. Right. Okay.
Your case, look necessarily for my.
No, my surface is not form. In this SU3 example, they do, but no, they form a hypergroup. Yeah. That's right. They form precisely this double coset hypergroup of general, fusion ring by D or whatever.
Right.
Yeah.
Is the choice related to the choice of the FTP?
The fact that I have to do CFTs instead of TFTs?
Start from a boundary parameter.
Yeah.
Then you have to do some TFT.
Right.
But you have a choice. And you go to TFT the same amount many times.
No. The bulk is completely determined. The choice is the other way. Once you fix the bulk, there's many choices of boundaries. But once you specify the boundary chiral algebra, the bulk is completely determined. It's the anyons are the representations of B, basically. Yeah. Thanks for the question. Right. So the upshot is you can either work with this non-faithful action via topological lines, or you could sort of work with the true action, which is by these domes. And this acts faithfully. And so as I alluded to, if you calculate what this hypergroup is in this SU3 example, you get Z2. But hopefully I'll have time for a non-invertible example. Yeah, let's do this. Mathematics, actually. Not proved by me, but by some combination of recent and Dom collaborators. I can tell you afterwards. Good. So one comment is that you can generalize this discussion. So in absolute theory is, we know that on top of considering just this encircling action, There's a more general action which incorporates the twisted sectors, which is this action by lassos, which is an action of the tube algebra of the fusion category. And so my claim is that in relative theories, the analog of the tube algebra is something called the dome algebra. It looks something like this. It also incorporates the twisted sectors. And it's really funny. I drew this picture and I decided I want to call it the dome algebra. And I just frivolously sort of Googled dome algebra just to see if it existed. And these people had already defined it and called it the exact same thing. Even though, as far as I can tell, they never actually considered topological surfaces, really. So this is like the domiest dome algebra you could possibly write down. Okay, and I'm not gonna like get into the details, but somehow like all the things you know about the tube algebra are basically going to be true about this dome algebra. For example, one small thing is that the representations of this dome algebra are in one-to-one correspondence with anyons of the sim TFT. And the sort of physical interpretation of that is if you take a twisted local operator O and you try to represent it in the sim TFT picture, generally you'll find that there's an anion sitting here. And that anion is telling you what representation this operator O transforms in with respect to this dome algebra action.
But just to be clear, the thing you were doing was not simple.
Well,
Because the bulk is chiral.
no. Well, it's a generalized sim. It's a relative sim TFT.
Okay, but there was no like gap symmetry boundary.
There was. It was this interface. So this is. It does. Okay, the claim
The
is that
interface exists.
anytime you have a fusion category of boundary topological line operators on a relative theory, you can turn it into the picture on the left.
Yes, but even on the picture on the left, like it doesn't end at the interface. Like it just goes on.
That's why it's a relative sim TFT.
Yeah. Okay. So sure.
Yeah. It's a generalization of the sim TFT where you allow the left to go on. Yeah. But otherwise,
the picture you had on the last slide that we just saw. That one was an actual sim, like absolute. So
I don't remember what I had.
No, this one. Oh, okay.
No,
it's okay, it's an interface. Okay.
Yes.
Your sim TFT is dimension. Other dimension are 3 plus 1.
2 plus 1.
But your the signature in 2-dimensional order, then the sim TFT.
It's a symmetry of a 1 plus 1D relative theory.
Okay.
And the sim TFT is a 2 plus 1D topological order.
But I guess this is
block order about 2 plus 1 signature 3.
Yeah. I'm not describing a sim TFT of a symmetry enriched topological order. I'm trying to describe a sim TFT of the boundary of this 1 plus 1D chiral algebra, basically.
Boundaries for here is the
This is again.
so the very first we had the similar structure. Right, the actions. Those are the top.
Yeah. So layered surfaces. Layered surfaces are these S's precisely, and I'm I guess exploring how they interact with parallel.
The region piece that they have in the files.
Yeah. So my TQFTV is this hypergroup symmetry enriched topological order.
Yeah.
And the claim is that the reason it's a hypergroup symmetry enriched topological order is because the boundary admitted a hypergroup action. It's sort of like a generalization of the inverted oracles.
Yes.
Yeah, great. Okay, and Leia already discussed this, but just to say that this grading isn't just like a grading, it also controls the fusion rules in the sense that if you look at how much of the quantum dimension of x times y lives in a particular component, the sort of fraction of that is given precisely by the structure constants of the hypergroup. And you can just check that if the hypergroup is in fact a group, this precisely coincides with the notion of the G grading. And indeed, so for example, in this SU3 level 1 example, the hypergroup of Z2 and Tamara Yamayama Z3 is a Z2 graded extension of Z3. And there's a pictorial proof actually of this hypergroup grading, which is too complicated to give, but I'll just flash a picture so you know it exists, but I'll read the paper if you want to understand. Okay, so really, so one thing I want to emphasize is that like your favorite thing about symmetries of absolute theories has an analog for in this relative setting. And just because it'll help me construct this non-invertible example in a second, let me just give you one example of a thing that generalizes from the absolute setting, which is this notion that symmetries sort of behave well with respect to gauging. So for example, in an absolute QFT, when you gauge a symmetry, the gauge theory itself has a dual symmetry that you can gauge to go back. The sort of like first example of this was in a paper of Boffa where he showed that if you have a 2D CFT with a Zn symmetry and you gauge it, then the orbifolded theory itself has a Zn symmetry that you can gauge to go back. And okay, so to sort of understand what our notions of gauging are in this relative setting, let's remember what the orbifold procedure looks like in the absolute setting. So in the absolute setting, there's sort of two steps. In the first step, you pick your symmetry and you restrict to the states that are invariant under the symmetry. And then in the second step, you sort of add in suitably defined twisted sectors. And why do you need to do both steps? Well, the sort of usual answer that's given is that you have to do both steps because of modular invariant. So if you did only one, let's say you did only the first one, then you get a theory that's not modular invariant, and that's bad. But relative CFTs anyways are not modular invariant. The bulk spoils modular invariance. So actually in this sort of more permissive setting of relative theories, we're allowed to contemplate doing these two operations independently from each other. So even just doing it for invertible zero point gauging is, I think, interesting enough. So let me review that. So again, suppose you have some chiral algebra and you have some fusion category C of topological lines, and I pick some symmetry group G of that chiral algebra. So remember I told you that once you fix a G symmetry of the boundary, you also sort of induce a G symmetry enrichment of the bulk. So that in particular means that you're allowed to gauge the bulk. And in fact, the operation that I want to do is I want to gauge this G symmetry of the bulk, but in the presence of this G-symmetric chiral algebra boundary condition. And the claim is that when you do this, the bulk goes over to the usual thing the bulk goes over when you gauge a G-symmetry. And what the boundary goes over to is the boundary, you sort of project down onto the G-invariant states effectively on the boundary.
So this would be very different from what you just described in the previous slide for absolute theories, where the gauging would correspond to not touching the bulk, but just changing the symmetry around.
Well, sorry, there is no bulk in the previous slide for absolute theories, right? It's just a 2D theory and...
Right, but if you wanted to interpret in terms of SymTFT, then you would say the bulk is just the same 2 + 1 DTQFT, but you're just changing the
You're mixing up two different bulks, I think. Maybe
maybe it's this.
Maybe I'll compare it to the thing you're saying, maybe offline, if that's okay. Yeah. 5 minutes, okay. So what's the dual category of topological lines on this VG chiral algebra boundary condition? And so to describe that, let me just note that G acts on the boundary lines. So remember, this G symmetry is implemented by surfaces that can anchor on the boundary. And so I can just sort of take a half cylinder of this G surface and I can surround any boundary line with it and produce a new boundary line. Technically, a G action involves not just that, but some sort of further coherence or structure maps, which are sort of like the numbers you get when you do these kinds of manipulations, but these are details that don't matter. And so, right, so what's the idea? So the idea is, in general, you orbifold by inserting a mesh of topological defects. And the way that you determine kind of like observables or objects of the orbifolded theory is you sort of ask, what are the objects in the original theory that kind of play well with respect to the mesh? And so in this case, the answer to that question is implemented mathematically by this notion of G equivariantization. So you want to at least look for G invariant objects in the original category, but also you want to keep track of a choice of isomorphism from Gx to X.
Sorry. Is it reasonable to say the gauge field, the system and control that?
Fix the gauge fields and couple the matter. Probably, depending on what exactly you mean. I think, yeah. Does it matter for you the boundary, or maybe you could ask your question again?
Okay, so we are talking about the gauging process.
Yeah.
I want this magic system, and that is from gauging by first find your gauge field and then couple the measure to the gauge field. Your opinion, it is zero.
Yeah.
I wonder whether the understanding might be the same way.
Yeah. The matter theory here is this relative theory. You know, it's the theory on the left here. It's this, if you like, it's this bulk TQ of T, but in the presence of its boundary condition. And then I introduce G gauge fields, and then I couple them. And after I do that, I get this thing on the right. So it's exactly what you had in mind, yeah.
Yeah, but somehow it must be the gauging. It must be the gauging to the bottom and up together.
Yeah, that's right. You do it together. So that's the idea behind this picture is you insert the mesh, and not only do you have to say what the mesh does in the bulk, but you also sort of have to say how it terminates on the boundary. I ran out of time to produce a picture, but Claude did a pretty good job compared to my picture. What's the interpretation of this phi, this equivariant structure? Well, it's sort of like it's a choice of top logical point junction where the mesh meets this line. So you want a G invariant line along with a way for the mesh to meet the line. That's what it means to play well. And this phi needs to satisfy some covariance conditions. Okay, so there's a lot of questions. Could I go 5 minutes over? Oh, thank you. So let me just make some comments on this like Hagroth problem. So the kind of open problem in this field of vertex operator algebras is to find a chiral algebra whose representation category is the Drinfeld double of Hagroth. Hagroth is this fusion category that's sort of considered to be exotic in some sense, in the sense that you can't construct it by the sort of usual ways of doing things. It has these fusion rules, and I'm not going to solve this problem, but let me just state various like reformulations of this problem. So one reformulation that is known is that, well, okay, so first of all, because this is a Drinfeld double, the central charge of any VOA that realizes this category has to be a multiple of 8. So the minimal possibility is that it exists at C equals 8. And then it turns out you can show by a sort of SimTFT argument that this VOA exists at C equals 8 if and only if the E8 level 1 chiral WZW model admits an action by the Hagroth fusion category. And the argument is just that if you found a Hagroth VOA, you could use it as a physical boundary condition in this kind of SimTFT construction. You're guaranteed to get E8 level 1 because that's the only sort of chiral CFT at central charge 8. And this would give you a Hagroth symmetry simply because this gap boundary condition supports Hagroth on its boundary.
So you would want to find the way, and after the parameterization is sort of the section of the center.
I haven't said anything about equivariantization yet. But yeah, in a sense, yeah, okay, good. It should be basically equivariantization. Yeah, that's right. I guess what I'm saying is that the Hagroth VOA would be a Hagroth equivariantization of E8 level 1.
Yeah, but no, E8 at least in 2.1 is like vertical so called.
Yeah.
But there action or
how it's related?
Yeah, how or other vertical.
Well, okay, so let me just say I don't have a Hagroth symmetry of this VOA yet. I don't think anybody does, but Yeah, I'm actually realizing Hagerup on the boundary, not really in this invertible. I don't think there's much to say about Hagerup playing with the invertible pole. Yeah, thanks for the question. Okay, so I just want to tell you a somewhat more, a variation of this kind of statement, that Hagerup UA exists if and only if some other theory has some symmetry. And the idea is the following. So Hagerup has this non-anomalous C3 subcategory. And E8 only really has a single non-anomalous Z3 symmetry up to conjugacy. So if it is to have Hagerup symmetry, then the Z3 part of it would have to be completely fixed. So you might say, okay, because that part is fixed, let me get rid of it. It's kind of boring. So let's imagine now doing this Z3 gauging of E8 level 1 in a 2+1D sense. So what that would give you is, we know that the fixed points of E8 level 1 with respect to the Z3 is the SU3 level 1 times P6 level 1 chiral algebra. So you'd get this, this theory after gauging. And it lives on the boundary of Z3 digraph width theory or Z3 gauge theory. And the question is, what lines live on this boundary after you've done this Z3 gauging? And by the sort of general abstract nonsense I told you on previous slides, the thing you have to do is you have to equivariantize Hagerup by this Z3. And if you go through this exercise, you find that you get what's called a near group category, which is kind of generalization of Tomura Yamadami categories. And the particular near group category looks like this. In addition to the sort of Z3 times Z3 worth of lines in the bulk, there's one additional line, L, which is trapped on the boundary. And it's invariant under all the bulk lines. And when you fuse it with itself, it gives this thing over here. And if you calculate the sort of, that's not going to act faithfully on SU3 level 1 times E6 level 1, but the sort of double coset hypergroup will, and that hypergroup is this kind of funny hypergroup with very irrational structure constants. And so the claim is that you get a variation of this statement I made on a previous slide, which is that a Hagerup UA exists at C equals 8, if and only if the SU3 level 1 times E6 level 1 chiral algebra admits an action by this particular funny rank 2 hypergroup symmetry. We're just having fun. Okay, so I don't have time to tell you about the non-compact example that was asked about earlier, so maybe I'll just finish. So, right, so as was anticipated by Yunchen, like it's hard to construct conformal subalgebras, and likewise, it's very hard to construct symmetries. And so we need better ways to do that. And part of the issue is that there's not really good definitions yet. So for conformal nets, there are definitions, but it's really hard to use conformal nets to understand examples. They're better for like proving abstract theorems. And for VUAs, nobody has managed to write down what it means for a hypergroup to act that isn't just like pictures that I drew. So it'd be nice to sort of improve that situation. And good. And there's a general expectation that sort of any fusion category C of topological line operator that lives on a chiral algebra boundary condition should admit the structure of a hypergroup cross-braided tensor category, which has not yet been defined aside from the case that the hypergroup is a group. And I mean, there's been a lot of progress towards the definition as we saw in the previous talk, but I believe it's fair to say that not all the axioms have been written down. And so that's one of the things that we hope to report on soon. That's work in progress with Sven Muller, Ingo Runkel, and Yifan Wang. And then finally, as was sort of asked about earlier, it'd be nice to drop very strong adjectives I use throughout this talk: finiteness, bosonicness, unitarity, rationality, and so on. Okay, thank you very much for your time.
We had a lot of questions during the talk. There's only one last question. Yeah.
So with your spirit fraction thing, it looks like this hypergroup is somehow like a zero categorical shadows categorical thing. First, why is that the right thing to do when you feel like you're using information by doing that?
Yeah, the hypergroup is certainly a zero categorical shadow of this thing that I want to call this hypergroup cross-braided tensor category, which is a one categorical thing, but maybe you could phrase it as maybe you could phrase it as an algebra and some kind of two categorical thing. So there probably is a two categorical viewpoint, which I'm not smart enough to understand. So I tried to do everything at the one category level eventually. You're right though that the hypergroup is zero. So in that sense, it's not all the way there yet. But yeah, my hope is that you can get a complete answer formulated purely in terms of one category stuff.
So thank you very much.
Thanks.
Yeah.
Yeah.
It's
Controlli. Tablo A e questo, tablo più e sono pieno. Per alzarlo, molto bene. E questo qui lo schiaccio, fa per fermarlo, te lo puoi fermare, chiedi arrest. Vai. Arrest. Vuoi fare super facile? Poi, questo dite, basta campo. C'è una certa lavagna, due arti differenti, una certa lavagna, sempre dentro, che però se la usi con la coppia, sono le prime 2 secondi. Quindi può andare fuori. No, non può andare fuori, la seconda può andare fuori. La prima va in alto, no? La seconda arriva a metà strada e poi hai la terza.
Però la terza magari la uso anche io.
Esatto, la terza è quella di 10 minuti e sai che puoi andare su quella. Per farla scendere, proprio se qui era nero una volta. Adesso è. Yes. Yes, because I was thinking that I was very no, I'm by triangle that is sitting there. Oh, I don't know how it is.
Okay, great. So let's get started with our last talk.
It's coming out of
All right, let's get started. So our last talk is by Andrea Antinucci, telling us about the twist on scattering from protected analysis.
And thanks a lot. Thanks for the invitation to speak here, and thanks to everybody for resisting until the end. So let me give some context. So, by the way, this talk is based on this written paper that I wrote with Christian, Giovanni, and Giovanni. They are all here, and also a previous paper. So, what is this talk about? It's not about hypergroups. It's about scattering. And the setup we work in is that we want to scatter some particles or some wave packet. So we have our space.
There's some business.
Great. So now that we have the better shocks, we can really get started. Yes. So we prepare some wave packet at time minus infinity. So we have fine. And we want to scatter it off some very heavy impurity. Okay, so we have some very heavy object that stay somewhere. Better shocks. Okay. So we have our in state. We scatter our in state, and we ask what is transmitted, what is reflected. So we are looking for the outgoing state. And this heavy object is this picture. So there is a fact that has been realized many years ago and in many recent papers. It can happen that the ingoing state lives in the antibody Hilbert space. And by this, I mean, for instance, if you have a weak couple theory, the antibody Hilbert space is the ordinary Fock space that is created by acting with the radiation annihilation operators. In other context, if you have a massless theory, strictly speaking, the arithmetic is not well defined, but you can, for instance, in free conformal field theories, this Hilbert space is going to be isomorphic to the vector space of local operators. But it can happen that the outgoing state does not belong to the same Hilbert space. Okay. And there are many examples of this, mostly in free theories involving fermions in 2 dimensions. But this problem is also related with scattering of monopoles in 3+1 dimensions. And it's a rather surprising phenomenon, because if you're doing your experiment and you're measuring the radiation at infinity, you're sending something in and you expect to be able to measure something that is living in your physical Hilbert space. On the other hand, you're observing some radiation whose quantum number are not matched by anything in your asymptotic Hilbert space. Okay? And in concrete examples involving free theories, free conformal field theories, people realized that in fact this outgoing state can be interpreted as being created by not from a local operator, but from an operator that is living at the end of a topological line. Okay, so it's actually a state in some twisted sector. So the goal. So first of all, I will dub this phenomenon with a word that is not completely appropriate, but not that bad. In the term of categorical scattering. And the goal of this talk is to go beyond the simplest example that people studied mostly in free theories and in massless theories. So to go beyond free theories. Including mass theories. And also to understand conceptually how is this phenomenon possible? Because as I said at the beginning, it's kind of puzzling to have a scattering process in which the ingoing state is living in a Hilbert phase, and the outgoing state is living in a different Hilbert phase. Because the time evolution is supposed to be a unitary map in a given Hilbert phase. So we want to explain why, in this context, this phenomenon is allowed. And we want to be able to predict this phenomenon in contexts that are not exactly solvable. Okay. So, as because of if it's not clear whether we will get to the end of the talk, let me give you the bottom line so that we don't get there. Is what's the answer? The explanation. So, in this context, it's extremely useful to model this heavy impurity that of defects. And just to clarify the terminology, because there are many different backgrounds in the audience, whenever we say defect, in general, I mean that it's an extended operator that is not topological. Okay? Then symmetries will be implemented by topological defects, but these are of special type. And the bottom line is that this phenomenon can be seen as a consequence of how the bulk symmetries are realized in presence of the defect. And there are two key concepts that I will like to explain that are the one that predicts the existence of this phenomenon. One is symmetry reflecting defect. The particular realization of bulk symmetries on the defect that I will explain. And the other, that of defect anomalies. And we present an argument after I introduce this concept that given these two elements, this phenomenon of categorical scattering is allowed, in the sense that it is an allowed channel of scattering. And in many of the special examples that people study in the literature, is actually the only allowed channel. So by knowing this fact, you predict the existence of the categorical scattering. But in other examples, it's one of the allowed channel, and we take the viewpoint that is the ordinary viewpoint that people have in quantitative theory, that whatever is allowed at some point will happen. And in fact, we will check in some solvable examples, I will explain one, that after we give the prediction, the phenomenon actually happens. But then you can take the more general viewpoint that even in non-solvable example, we have a prediction for the phenomenon and an explanation for why the phenomenon is supposed to happen. Okay. Other question on the introduction? Okay. So let me start. Okay, great. So let me start explaining what I mean by defect-based symmetry. So the context. By the way, some of the concepts that I will introduce are valid in any dimension. Then the explicit examples and some of the things that I will say are only valid in 1 + 1 dimensions with one-dimensional defects. Okay. But for the moment, the context that we have some bulk theory, that is dimensional theory, with some symmetry S. So the symmetry is implemented that we all know and love by topological operators. And then we want to study our theory in presence of an extended defect. So we have a defect of some dimension, P, okay? And we can ask what is the fate of the topological symmetry operators in presence of the defect. So in particular, you can study a configuration in which the symmetry operator is crossing the defect. And in general, while you will be able to move the defect, the symmetry operator away from the defect, the junction here might fail to be topological. Okay. So if it is not topological, we say that the symmetry is broken in presence of the defect. Okay. While if it is topological, we say that the defect E is S-symmetric.
Ask a question.
Yes.
If the dimension of the symmetry operators and the dimension of the defect are such that the generative intersect,
Yeah.
you just say they're symmetric by the set.
Yes. Without what can be destroyed. It's not optimal, but I will not use this game. Good. So a small caveat is that sometimes you might need to draft this junction with some degree of freedom on the defect to make it topological. So then the naive junction is not topological, but then you can dress it with something to make it topological. So if it is possible to do that, then we say that the defect is symmetric. Okay. Good. Now there is a stronger situation. Yes.
Is that an extra predicated like explicit or spontaneous?
The bulk has the symmetry. So the bulk is symmetric.
When we say that the symmetry is broken, do you mean explicitly?
It's explicitly broken by the presence of the defect. To insert the defect in a correlation function, then the theory in presence of the defect is no longer symmetric. Okay. So there is a special case when the defect is codimension 1. If the defect is codimension 1, we call it an interface. We have our interface D, codimension 1. Now we can consider the more general situation in which we even have two different theories on the left and on the right of the defect. In principle, they can even have different symmetries. So in this case, the most general situation in which we might say that the defect is symmetric is that there exists a topological junction between a symmetry operator from the left and a symmetry operator from the right. Okay, and this point here is topological, and we can move it. But now there are actually interesting notion for us. That is one of the symmetry reflecting defect. We use symmetry reflecting defect. Is when we can have an interface such that the topological symmetry operator from one side can just terminate on the defect. Okay? And they terminate in a topological way. So we have a semi-local operator here that is the endpoint of a topological line in the bulk. It's a defect operator and it's topological. Okay? Now, okay, this equation implies this one, but the vice versa is not true. So this is a much stronger equation. And one particular case is if the defect is product of boundary conditions, then it's obvious. But it's not the general case. And in fact, you can view the symmetry reflecting defect as a sort of Faraday cases. So they behave like boundaries, but only restricted to the symmetry sector. So charged object cannot escape from the interface, but uncharged object can. Okay? And in fact, let me make a few remarks about the symmetry reflecting interfaces. It will be important. So the first one is that we have much more powerful selection rules in presence of symmetry reflecting defects. The selection rules are such that even if we consider a single theory on the left and on the right, like in this situation, the charge for this symmetry must be conserved independently on the left and on the right. Okay. To make this more precise, we consider a correlation function with a bunch of operators on one side, the defect here, and a bunch of operators on the other side. Then the total charge, in order for this correlation function to be non-zero, the total charge of this operator must be 0. The total charge of this operator must be 0. So it's not allowed that the two charges cancel each other. Okay? Here. And in particular, you might understand it intuitively from the point of view of the defect, if it is symmetry reflecting, and the bulk had some symmetry S, effectively the defect has two symmetries. S left and S right. Okay? And in particular, that means that if we start coupling our symmetry to background fields, the most general background field is a pair of background field on the left and on the right. Okay? So we have this doubling of the symmetry, so this equation is much more powerful. Okay? Any question about this? Okay, good. So let me. No. Great. So the other concept that I need to introduce is the one of defect anomalies. So yesterday somebody said that there might be a 7 definition of anomalies. So we did my definition. One that we use. So in general, what do we mean by a theory having an anomaly? We mean that if we consider the rotation function of our theory coupled with some background field, we perform a gauge transformation, it is not invariant, but in general, we can phase in some local phase space-time. Okay? Yes. Yeah.
In the case of the symmetry reflecting amplitude and the chance to charge the value of the side. Take one operator from the left and move it to the right.
What do you mean? The operators are not topological.
They are not topological.
No. So just local operators that are charged on
in the interface. The operator move it.
Yes.
And then it off the interface.
Yeah, and considering different correlation function, yes.
It becomes a different correlation.
Yes. And this correlation function must be 0 if that operator was started, because now you are matching the symmetry on the left and on the right, but this correlation function must be 0 now. Okay.
And also with operators.
No, I'm interpreting this question by just like looking at a different correlation function in which one of the operators is on the other side, and I started with the same set of operators. Now, in the same set of operators, we're satisfying the selection rule, and I move in one operator that is charged. Now I'm wrong with satisfying the selection rule, so the correlation function. Good. So this is the general definition of anomaly, but now what happened if I consider a situation in which I have a defect? So now we should consider the defect function, and it can happen that in presence of the defect, gauge transformation gives an additional contribution here that is localized on the defect volume. And this object is what we call defect anomaly. It does not require the existence of a bulk anomaly, so it can exist independently. It's an anomaly that only arises in the presence of a defect. Okay? And as for ordinary anomalies, they can be cancelled by inflow with a bulk that is 1 dimension higher, but now it's 1 dimension higher than the defect. So it will be a p plus 1 dimensional bulk. Okay? In the invertible theory, whose boundary is the defect. Good. Now, currently, we can take a topological line view, but yes.
If there's a fault, anomaly, so is there an ambiguity in separating them because make some fluid definitions shift it?
I don't think so. They are of different dimensionalities. So in which case? It depends on the dimensionalities. So probably if this is dimension 1, it can happen maybe because you can reabsorb with a counter there. There is a map.
Also, spread the scene. If you are breaking the scene, then you have a long sequence.
So if it's breaking the scene, you cannot even consider it. This is not trivial, that it's not. Okay, you stop. I don't know.
The good defects, don't make the same.
Yeah, no, there is but we don't know yeah. If there's not in the file, you have to ask whether. Okay, anyway, we can have a slightly different viewpoint that will be important for us. That we consider a defect here, for instance, here during a 1+1 definition. A defect anomaly means that the symmetry operator that can plot the defect topologically, one here, pretty here, okay, maybe. So I have two topological symmetry operator crossing the defect. If I try to exchange them, suppose the symmetry is abelian, so if I do that in presence of the defect, there is no problem. But in presence of the defect, it might happen that I exchange them and I pick up a phase. Right? And this phase is related with the defect anomaly. So the a non-trivial phase here, the signal of a defect anomaly. This viewpoint will be very important for us.
So
Yes.
this is just a symmetry question.
In this case, yes. In this case, yes.
More general.
Yeah, because in this case, I'm in 1+1D with lines, and that's true. But more generally, it's not. If you are like in 2+1D and this is a surface, that's yes. In fact, here you can view this a signal, an extension of the symmetry by this cycle. Good. And in fact, I guess you are not surprised by the statement that in this context, in 1+1D with defect lines, defect anomalies are in 1-to-1 correspondence if you have a symmetry group G with H2 BG1. So are like anomalies in one dimensional, are like anomalies in quantum mechanics. Okay? What is more interesting, however, is what happened for defect anomalies for symmetry reflecting defect. As I told you before, effectively, symmetry reflecting defect has two symmetries. So you might suspect that in fact the anomalies for a symmetry reflecting defect are given by anomalies of the product symmetry. And this is actually true. And you can understand this by thinking about the background field viewpoint. So you need to couple two different background fields. So you can have different anomalies, and you can write more topological actions involving two independent background fields. So for defect anomalies for a group symmetry in this case, in the case of symmetry reflecting defects, the anomaly will be labeled by. And in general, if you have two different theories on the left and on the right with different groups, you'll have G left. And what is the analog of this viewpoint? Well, it's very simple. Because now we can terminate either from the left, a symmetry operator from the left and a symmetry operator from the right. I can exchange them. And now I can also get space. Yeah, that space was one. Okay. And this is our defect anomaly in this case. Now, a simple example to show that this is something that exists. This picture might remind you something, but so a simple example is really trivial, but it illustrates the idea, and we come back in a more complicated example at the end of the talk. We consider
But in the cycle chi, since it takes like
A from the left, GL, and E from the right.
Yes.
But the general cycle can take also two bytes from the left.
Yeah, but it's not a general cycle.
Yeah, I agree. It's the junction.
So you can agree.
I think the junction, outside, inside.
Exactly. This will come back. Exactly. This will come back. It will be very important. Yeah, let me show you the example.
Should be able to false. General.
But the other co-cycle will be related with the defect anomaly of a single side. You want the one in which you just have one from the left and one from the right, sort of a mixed anomaly. Yes. And just illustrating this one because it's the one that will be important for the starting situation. So using CFT, we all know the CFT, we know the topological defects, and we know that there is a duality defect. So this is a defect, in this case it's topological, fine, it's not general case, but they exist. And I can consider this as an insertion, so it's case in CFT also has zero symmetry. And as we all know, the duality defect is able to absorb the zero symmetry line. So we can regard it as a symmetry reflecting defect property. Okay, so this is the two line. Can terminate topologically on the defect. And we know that we have one of them from the left and one of them from the right. We exchange them. It will become minus signs. This minus sign, in this case, is an F symbol of the integral category. Okay? So in this very special case, the F symbol can be interpreted as a defect anomaly, or the duality defect interpreted as a defect in the. Okay.
The formal interface is that kind of classified paradoxes.
Yeah.
Are there any non-factorized models that are symmetry reflected?
Are there but not non-topological?
Non-topological.
Yes. Yes. Okay. Yes. You can start from this, add some deformation, flow in the infrared, and you will get some conformal interface of easing that provides this. Okay. Good. Now we go back to sculpting. How much time do I have? 40 minutes. Ah, great. So. Well, the first puzzle we want to address is how is it possible to prepare some in state in the asymptotic Hilbert space and get some outgoing state that is a different Hilbert space. They're supposed to be in different superselection sectors. So how can they be connected? So the resolution of this puzzle is either trivial or might be surprised, depending on whether you thought about this before. But at the end, it's extremely simple. Because I was talking about the asymptotic Hilbert space that is constructed using bulk operators. But in presence of the defect, you actually need to consider the defect Hilbert space. So this is not the right space to consider. Consider the defect Hilbert space. So the Hilbert space that you obtain by quantizing your theory in space. The Hilbert space that you obtain by quantizing your theory, presence of a defect extending out time. This will modify the Hilbert space, and that is the right Hilbert space. Okay. And now you can ask, well, before I was saying that you can prepare some state at asymptotic infinity that is in the Fock space and get something that is in some twisted Hilbert space for some symmetry. So you should compare this Hilbert space that you obtain this way with the Hilbert space that you obtain by further twisting with a symmetry operator. So what happens if I consider a defect here, but also a symmetry operator? U. In principle, you should produce a different Hilbert space that is a defect twisted Hilbert space. However, this topological operator here can be moved on top of the defect So canonically, this is isomorphic to the Hilbert space that I obtained by fusing the two. So if I replace my defect, let's say this one is isomorphic, sorry, the twisted defect Hilbert space, twisted by U, is isomorphic with the Hilbert space obtained by fusing my defect with the topological symmetry operator. However, if you remember the definition of a symmetry reflecting defect, you assume that this is symmetry reflecting. Now, this is nothing but the original defect Hilbert space. Okay? So these two Hilbert spaces are actually the same, and that's the reason why, in presence of this impurity, it makes sense to prepare an in-state, the asymptotic Hilbert space, and get something that naively seems to be in some twisted sectors, but it's actually not. Because once I consider the defect Hilbert space, they do live in the same twisted sectors. Okay? Yes.
I'm assuming that the smallest case between D and U and D again is not the
D, U, and D again.
The
No.
topological defect to the joints.
I could have multiple topological reductions.
The ISO is so the isomorphic is non canonical and
Yeah, it might.
Yeah,
Exactly. Yeah. Yes. Great. So now we concluded that in order to have even the possibility of having categorical scattering, we should consider scattering of symmetry reflecting defect. Categorical scattering of symmetry. Now you might have a second puzzle, because as I told you before, in a symmetry reflecting defect, the charge cannot go out, and as the word suggests, it should reflect the charge, but doesn't really. So let's consider preparing an incoming state that is charged under our symmetry. Charged under our symmetry G. Okay, and our defect D is symmetry reflecting under G. Now, what are the possible outputs? Well, for sure, there is possibility one in which we send our ingoing state, and we have reflection. So let's say we have some ingoing charge, wing, and we have some reflection that carries the same charge. Q out equal to Q in, and we might also have some transmission, but it's G neutral. Okay, this is of course a possibility because I'm satisfying the selection rule that I told you before. But this is kind of a boring possibility, not the one we are looking for. The interesting fact is that there is a second possibility. There is a second possibility on top of this. So let's say we have 1, 2, 3. That D carries non-trivial defect anomaly. And let me emphasize, I want a G defect anomaly that is of the type that I was telling you about before. So sort of like a mixed anomaly between the left symmetry and the right symmetry. And why? Well, exactly as was anticipated by Leia 2 minutes ago, I can interpret that fact by saying that the topological junction here of one symmetry operator terminating from the right is charged under the symmetry operator from the left. So I have a point operator that is a defect operator semi-local, so it's the endpoint of a topological line, and it's charged under the left symmetry. Okay, so this carries some charge. Carries some charge that is determined by the defect anomaly. So I can have certain charges in my model. Okay. And maybe now I can go to the last method. So I'm going to do that's great. So I hope everybody can see it. Great. So now, what is the possibility number 2? The possibility number 2 is that I prepare my ingoing state. There's some charge. And it I can also have some reflection. But say that the reflection now is neutral. It can also be non-neutral. And the outgoing state. So now, assuming that the reflection is neutral, in order to match this ingoing charge, I need to have something on the defect. And I will make this assumption that the defect, I'm considering elastic scattering, and the defect is simple, so it doesn't support topological local operator on top of it. So I cannot just generate a random topological operator because they don't exist. And then, in order to match the charge here, the only possibility is that I generate a local operator that is attached to a line on the other side. And this can match the charge because of the defect anomaly, as I was explaining before. Okay? So this is I have some draft charge that equates the ingoing charge. But then in order to have this, I also need to have something here. So the outgoing state lives naively in some twisted sector. It doesn't really live in a twisted sector because, as I told you, the twisted sector here is isomorphic to the untwisted sector. But let's say that the outgoing state is created by an operator that lives at the end of a topological line. And this is exactly the phenomenon that I wanted to. Okay? Questions? Okay, good. If there are no questions, I will discuss one example. How much time do I have? Great. So we quickly discuss one example. Yes.
What there is we have a loop G and we have a anomaly here to such a what is the algebra of this defect interface? Is it kind of
well, it depends. Sometimes, in fact, you can interpret the anomalies as extension, yes. So, but it depends whether you are considering defects, symmetry operator intersecting the defect or not. In the past, they will still use it. But then you can consider the algebra of topological symmetry operator that terminates on the defect, and it can be some extension of the original loop. That's right.
Yeah, I'm talking about like all the possible configurations which the topological defects are like horizontal, and they are attached the no quadratic such.
Yeah.
So then there's a set.
Yes. Yeah, sometimes you can have these extensions. For instance, the case I was considering before, I think you essentially get before, and because when you exchange two, but it's a bit strange to say because one defect is from the left, the other defect is from the right. So I don't know. Depends. You have to work it out like it.
Are you assuming that the space they have?
Yeah. Yes.
So it's not
No. Yes. Okay, so let me illustrate quickly one example. That is the easing fit theory. By that, I mean easing CFT defined by the energy operator. But I want to consider a setup. So I'll start from easing CFT, and I consider a defect in the easing fit theory that is obtained by, on the two sides, I consider a mass deformation that depends on x, and I can take it to be plot on one side and minus on the other side. So essentially, this CFT deformed by minus m epsilon and CFT plus okay. So this will define a defect. I can further address this object with the integral of the energy operator on the defect. Okay. So this G is a number. You can tune it for the purpose of what I'm going to say. In your mind, you can even fix it to 0. It doesn't really matter. But this defines some interesting interfaces between these two theories. And I don't have much time to go into the details, but so you can imagine if you take M to be very small, then these will, and if you set G to 0, let's first set G to 0, then this should define some defect in the CFT. And it turns out that that defect is the duality defect of this. Now, when you turn on the mass, this is not a topological interface. If you want, I can write down explicitly what is the F matrix in this case. So it's not a topological defect. But however, given that the epsilon operator preserves the Z2 symmetry, this defect will preserve all the properties of the duality defect of the CFT under the Z2 symmetry. So in particular, this object here turns out to be symmetry reflecting, and it carries a defect that way. Another way that is interesting to explain why this is true is that the heating field theory secretly is after fermionization is nothing but a theory of a free massive Majorana fermion. And what I'm doing is that I'm turning on negative mass on one side and positive mass on the other side. Okay. Now this theory it's actually free, so you can solve everything explicitly. You can write down the equation of motions and solve them. And it turns out, so after fermionization, if you solve the equation of motion, you can discover that there is a normalizable Majorana zero mode that is localized on the defect. So essentially, you look at the equation of motion and you find a zero energy solution that is one behave like this. On the side of the defect. So it falls off when you go away from the defect, it's localized on the defect, and it has exactly zero energy. Okay? So this tells you that the ground state in presence of the defect is twofold degenerate. And so the defect should support, in the fermionic picture, a topological local operator. However, given that this is fermionic, when you bosonize back, this fermionic zero mode is no longer gauge invariant. So it must be attached to a topological line of the dual symmetry. And the dual symmetry is the Z2 symmetry of the heating field theory. And so what we are saying is precisely that in the original theory, this defect must have a topological local operator here that is fermionic and is attached to a topological line. Okay? This is topological because it has zero energy, and moreover, given that it is a Majorana fermion, it's also charged under the Z2 symmetry of the heating field. That tells you that the defect is symmetry reflecting and it has now. So by our general argument, we can predict that in this context, if we scatter some state in the CFT that is charged under the Z2 symmetry, then there is an allowed channel. There is an allowed channel that is scattering something that is attached to the Z2 line there. So intuitively, this scatter state, the state, is prepared acting with the sigma operator on the vacuum, and then there is the possibility of an outgoing state that is prepared by the mu operator on the vacuum. This is just a possibility. It's not to scatter that you get that, because it's not a topological situation in which you send something in and you get a unique output. In fact, you can get multiple outputs. But given that in the fermionic picture, everything is free, we could solve this model exactly and show that there is in fact an allowed channel like that. The arithmetic is not free yet. Okay? Yes.
Instead of phrasing it in terms of scattering, could you just say that there's some non-vanishing correlator of like sigma on the left, mu on the right?
Absolutely, yes, absolutely, yes. Good. Yeah, in fact, the problem is that we are not sure whether there is a proof of the LHC formulas in terms of computation. Yeah, I don't think there is. In free theories, maybe you can, but in general, I don't think there is. People use it, but it's not clear whether it's always valid. But okay, anyway, so this is something that you can predict and you can check. And we also worked out many other models. So there were some previously worked out examples in massless equation, pre-massless situation. I think that Antinucci tomorrow will talk about some of them from a kind of different perspective, I hope. So we checked that with all the known examples, our general story applies there, and we can represent these results. We worked out this one, and one very interesting example that we worked out, and it's much more complicated, so I don't have time to explain it. It's a model that is massive, but it's not free. So it's a deformation of the three critical easing model in the bulk in presence of a boundary condition that preserves the Fibonacci symmetry. So the bulk here is integrable, and we found a particular boundary condition that preserves the Fibonacci symmetry that turned out to be also integrable. So the scattering process in presence of the boundary condition is also integrable. And there is a very similar story, like the one that I explained, that the boundary condition has a defect anomaly for the Fibonacci symmetry. So we could predict by our general argument that the categorical scattering was supposed to happen in that case. But given that the boundary condition is integrable, we could even solve the scattering and check that it was actually happening. So it was a nice result. And so basically, we conclude here by just saying that it would be very interesting to extend all these ideas to higher dimensions.
Thank you. So yeah, question.
So I think how to use this as picture to describe to understand the scattering wildfire of multiple by the S introduction.
Yeah.
How do I describe it there?
Yeah. No, that's one we would like to do, and we are thinking about it, but we don't know how to directly approach the problem in people. Yeah, it's very interesting.
Any other questions? Okay, let's think getting in. Oh yeah, tomorrow 7:30 at Brighton Earth. You have much.
You were in front of America.